Welcome back to Chemical Process Safety. This video is about a review of probability mathematics. The reason why I'm reviewing probability mathematics is because many components in a process are not just single components. The components themselves are made up of subcomponents, and the probability that each one of those would fail would contribute to the probability of the entire piece of equipment failing. So let's start with an AND gate. So a gate is just, if you took a logic class or something, a gate is what they would call the probability of two events either happening together or independently. Well, these are all independent events, I should say. That's actually a key assumption that we have to make. And that's what we'll continue to assume, that the probability of event one is completely independent from the probability of event two. And again, in real life, this would not quite be the case. But this is not a logic class, right? So we're going to make a simplifying assumption to be able to solve problems or to get some tractable answers. So P, by the example, is the probability of that event occurring. And also, by the way, the AND gate is given the designation of this tombstone shape. Sometimes you might see it oriented vertically. The OR gate will be kind of this Pac-Man ghost type shape, I like to call it. Again, could be oriented vertically. But the AND gate says that both event one and event two will occur. And mathematically, the way that you would figure out the probability of both of these things occurring is by multiplying the independent probabilities together. The fancy math way to say this is that P is equal to pi times P sub I. So take up all the independent events, you multiply them. That's what pi stands for, the multiplication of multiple things all together. And that is the probability of the entire system failing. So just as an example, I sometimes like to talk about this in terms of flipping coins, but because flipping coins only have two possibilities, it's either heads or tails. It's easier to see, but you might have a misconception based on that because the probabilities are equal. So I like to think about dice instead. And anybody who's ever played Monopoly or something, or craps or a game like that can hopefully understand these probabilities. So what is the probability that I roll snake eyes if I roll two dice? Well, the probability that the first dice will be a 1 is 1 out of 6. And the probability that the second dice will be a 1 is also 1 out of 6. So I multiply those together. Snake eyes is one of the rarer rolls for a dice game. It's 1 over 36. Furthermore, remember that the reliability and the probability are complements of one another. They have to sum up to 1. So I can also say that the reliability is equal to 1 minus P, and I just set up above that P is equal to pi of PI. So again, plugging in the expressions for that and rearranging can get me this expression for the reliability. The important thing, or the thing to take away from an AND gate, is the probability of a system failure for things that are connected with an AND gate is always going to be less than the probability of any one given event. And that is because so probability is a number that is less than 1. So anytime you're multiplying numbers that are less than 1 by each other, the result gets less and less and less. So think about this example. The probability of one dice being a 1, one die being a 1, is 1 over 6. But if I roll two dice, the chances that both of them are a 1 is 1 over 36. And if I added a third dice, I would get to 1 over whatever 36 times 6 is. But the point is, for AND gates, I can reduce the likelihood of system failure by connecting things with an AND gate. And that's one of the biggest take-home messages of this module. In contrast, there's the OR gate, which is a little bit trickier to think about. But an OR gate says, what is the probability that either event 1 or event 2 happen? So if event 1 happens, event 2 does not quite have to happen. So going back to our dice roll example, what is the probability that at least one die lands on a 6? And whenever I ask students this, and my own misconceptions too, you tend to, I think the answer that you're probably thinking of is that it's going to be 1 6 plus 1 6. And I didn't write that answer because I wanted you to think about it, but that's not actually correct. And the way to see that, or the way to rationalize that, is that I can't simply add the probabilities of independent events, because What would happen if I rolled 10 dice and I asked what is the probability that at least one of them is a 1? Well, by the same logic that you said it's 1 over 6 plus 1 over 6, I'd be basically doing that 10 times, and then I'd end up with 10 over 6, which is a number. It is not a certainty that I would have one dice that lands on a 1. So this is not the correct equation. What you have to do is you have to take the complement, and then you basically run the complements as an AND gate. So how I like to think about this dice roll example is you can flip the question around, and instead of asking what is the probability that at least one die lands on a 1, you could say what are the probability that that both dice. See, how do I want to say this? So the probability that you don't get a 1 is 5 over 6. So that's the way to ask it. So instead of saying what is the probability that at least one die lands on a 1, you would say what is the probability that neither die shows a 1? And the probability that neither die shows a 1 would be 5 over 6 times 5 over 6. And then you would take the complement of that. So you would do 1 minus 5 over 6 times 5 over 6. And that would be the correct answer to this riddle. So again, mathematically, what you would do is instead of looking at the probability of failure, I would rearrange to get the reliability or the complement. So the probability that the event does not occur, 1 minus R1. Yeah, the probability is equal to 1 minus R1. And then the probability of 2 is 1 minus R2. And you would multiply the reliabilities together. So again, for AND gates, you multiply the probabilities. For OR gates, you multiply the complements of the reliabilities or the probability of not the thing occurring. Again, the mathematical expression is confusing to me too. I like to, again, think about it in terms of dice or cards or some other type of probability exercise. The other way to think about it too is that if things are connected with an OR gate, the reliability of the entire system requires all components to be reliable. In other words, if there are multiple things that go into making the whole thing reliable, and if only one of those things breaks, then the whole thing breaks. So I can express the total reliability by mathematical rearrangement. So just like the AND gate would reduce the component failure, things that are connected with an OR gate, because of what I just said, if one thing fails, the whole thing fails, is much, much worse than an AND gate. So AND gates are good, OR gates are not quite as good. In fact, OR gates are actively bad, right? Because the more components that you add, the more chances things will fail. So if just P1 was by itself, it would have a certain probability of occurring. But if I add P2, and if P2 breaks the system, well, now if P1 was still fine, but P2 breaks, now my entire system breaks. So way back in an earlier module, we talked about inherently safer process design, and one of them was simplification. That's what that was kind of heading towards, was trying to reduce the number of OR gates that are possible. But conversely, you could increase the number of AND gates by adding redundancy to your system. So that means two pieces of process equipment that basically do the same thing. So if I had one alarm, for example, but a backup alarm, and failure of those alarms going off would require both of them to fail independently, is a much more reliable system. This is just more mathematical stuff. So if I have any given two events, the probability that it happens is 1 minus P times 1 minus P2. And then I can FOIL this basically and say there are 4 scenarios for 2 events. And the 4 scenarios are: 1 is that they both fail, 2 is that they both work fine, and then the other 2 events are one of them failing while the other one works fine, and vice versa. In this class, like when we're talking about the failure of pieces of process equipment, the term P1 times P2 is usually generally much less than 1 or very, very small. So if that is the case, I can simply say the probability of failure is equal to P1 plus P2. And that's going back to if I just roll 2 dice, my answer is probably pretty close to 1/6 plus 1/6. but it would be even closer if I were rolling a 10-sided die or something like that. So the lower this P1 times P2 term is, the better this approximation becomes. And this is just a recapitulation of what my key thesis lesson is. So for an OR gate, the probability of system failure is greater than individual system component contributions. So again, if I'm designing a piece of equipment, you want to have AND gates and not OR gates. Let's see that principle play out with the following example. So let's say I have a pump, and that pump is the flow rate that is delivered by that pump is measured by a flow meter. And then that flow meter, these should be dashed lines, by the way, because these are electrical signals in my PNID that I'm hand drawing. If the flow meter talks to a controller, and then based on the value of this flow, if the controller either opens the control valve or closes the control valve, we can analyze for this entire system what the probability of failure for the whole thing is. So again, the system is composed of three main parts: the control valve, the controller, and the flow meter, and technically the pump too, but we'll assume that the pump works flawlessly, or we'll just look at the system of just these three things. So the way that I would do this is I would look up the mu, the failure rate in table 12.1, and I would find that the control valve has a failure rate of 0.6, the controller has a failure rate of 0.29, and the DP cell has a failure rate of 1.41. I can then convert those to a reliability, and for a lot of cases, we're looking at the likelihood of failure within a year. So the time frame of 1 year is oftentimes assumed. So remember, R is equal to E to the minus mu t. And so the greater this failure rate is, the less reliable it is. And that should make intuitive sense. And then the probability of failure is simply 1 minus the reliability. So I have to think about whether these things are connected by an AND gate or an OR gate. And if I inspect this and think about it for a second, if the flow meter fails, there's no possible way that the controller would magically know what the right value is for the flow, and it wouldn't work properly. So the flow meter causes the entire thing to fail if it fails. Similarly, the controller, if that fails, the control valve wouldn't necessarily know to open or close without the controller telling it to. So if the controller fails, the whole thing fails. And then finally, the control valve, if that fails, it doesn't matter if the flow meter is telling the controller the right thing and the controller is telling the control valve what it should do. If the control valve isn't listening, then again, the whole thing fails. So this is an OR gate connected. All three are connected by a single OR gate. So it would be three things all going into one. And so to calculate the likelihood that this fails, I need to multiply the reliabilities together. And then if I were interested in the failure probability, what I could do is take 1 minus the reliability. And I would conclude from this that within a year, I would expect this to have a 90% chance of failing over the course of the year. So this is a pretty bad design. You do not want to, there's no magic number, right? It's not like anything greater than 70% is awful or something like that. But certainly 90% is not very good. One final note, I can calculate the overall failure rate of the entire system just by working this equation backwards. So once I have the reliability, which I calculated up here, I can plug this in and get a mu value, basically, by plugging in t is equal to 1. So that's one way that I can calculate the mean time between failures for something where it's a system of combined components. So I'll wrap that lesson up here. Hope you enjoyed. I'll see you next time.